What we were trying to do in the EPRI model in 2006 is look back at the sigmas, and I'll only talk about essentially our comparison of standard deviations between active regions and stable continental regions. And the question here was, can we use the empirical data, basically, as opposed to stepping through all the modeling components that Gabe talked about with the issues of properly propagating all of the errors or variability without potentially missing correlations in the parameters. All right, this isn't going to work. Right. So from we had started out with the 1997 models that we were looking at. These are their standard deviations. This is at PGA, but at all the periods there was a magnitude dependence trend, whereas in the East, Toro's 97 model had looked like this, fairly flat with magnitude, but a big jump from larger distances to short distances, and that's part what Gabe was mentioning. This increase was due to the way the propagation of the variability was done, and this has a big impact on the close hazard from close-in sites. So that's about a 0.2 potential change in the standard deviation. Early on, so this EPRI study was done as the NGA work was going forth, and the early NGA models were showing a constant standard deviation for PGA of around 0.6. So we didn't have any magnitude dependence in there. That started to change, and Linda and Brian will talk about what has happened recently, and some of the models now also reproduce this effect. The EPRI report was not looking at, is the standard deviation magnitude dependent? That was not the question they were addressing. It's, can we take standard deviations from our NGA models and move them to the east? Just pick them up and drop them over there. Okay. So when we went through this and later on concluded we would show a reason why we think the Western U.S. sigmas are applicable, because at that time the sigmas were constant with magnitude. That's what we ended up using in the EPRI report. But that wasn't a topic that we dealt with. At different frequencies, this is magnitude 5 close in. This is our NGA models. This is what was coming out of EPRI. So this is this large increase here, 0.1 to 0.2 sigma units, is due to that close-in distance correction, and I'll talk about it in a bit. At larger distances here, now same magnitude 6, but 10 kilometers away, they're becoming more similar because the distance correction isn't as large. When we go up to magnitude 7, at 30 kilometers away, actually the EPRI models are pretty similar on average to what our NGA standard deviations were. So the issue when we're trying to decide what to do, we don't have big magnitude data in the East on which to compute the standard deviations. And so what we had done was looked at the two pieces that you are now very familiar with, our IntraEvent and IntraEvent standard deviations, to try to figure out if the standard deviations in the Western U.S. data were applicable to the East. We basically looked at teleseismic parameters that we could use as a proxy for what the actual event terms would be from ground motion. And so here we ended up using half source durations, and I'll show you that. The intra-event standard deviation really we did simply based on comparing parametric predictions or variability by changing different crustal structure models in the East and in the West, and looked at also those short distance adjustments that Gabe was talking about. And finally, there was a high frequency adjustment that I'll just mention. That is, when you start to get to the higher, in the West, frequencies above 10 or 15 hertz, you now don't have much energy in the record. There's nothing to resonate, and so the variability looks more like the peak acceleration variability than like response spectral values. So we needed to bump it up in that range. The first thing to just look at a crude way of saying that our source property is more variable in stable continental regions than in active regions. We use the simple regionalization that's used for the world and drop things into active regions here, stable continental regions, and what do we got? blue oceanic regions. But the key here is that we took a source parameter, the half duration. This comes out of teleseismic catalogs. These were from the Harvard catalog. So telling you the shorter a source is for a given magnitude, effectively we're getting a higher stress drop. You're compressing the energy release in time. So we use this as a proxy for what the variability of stress drop would do. And the key here is comparing stable regions versus active regions. We now want to know what is not its level, but what is its variability. So in the active regions, the standard deviation of those half durations were about 0.3 natural log units. And you get similar numbers based on different ways we could have done subsets of the stable region. So from this, we said, given this proxy of half duration as a measure of source excitation, we didn't see a reason why the inter-event standard deviation in active regions would be different than in stable regions. Okay, we lost something here. Okay, this picture would have had just the so Gail had gone through her data set and got stress parameters as a function of magnitude and looked at the standard deviation of those earthquakes. So there's a bunch of earthquakes here. If you look really hard, in the magnitude, say 4 to 6 range, giving you a range of stress drops. And actually, Bob Dara will cover all those. The key is, if we propagated that variability of stress drop into ground motion variability, you end up with an inter-event standard deviation of about 0.43. Okay? If we had looked at what the NGA models are now producing, they're in the 0.3 to 0.4 range. So these are similar. This is a little towards the higher end. This is actually near my end, which is about 0.4, and I think Ken's and Yusuf's models are the smallest at around 0.3. So in all of this, the other issue we have, our NGA models, as many people have mentioned, lots of extra parameters and coefficients, but that, and the big ones, say style of faulting and some things on hanging wall and footwall, have a really small impact on our standard deviation. We add all that complexity, as I mentioned this morning, trying to get a model that extrapolates properly to different conditions, not trying to change sigma. So I can move my standard deviation from numbers of 0.6 to 0.59 or something. Those are meaningless changes. So what we decided, based on the inter-event standard deviations, that the comparison of the standard deviations from half durations or source durations suggests that our NGA models are applicable in general. The question is the source duration any indication? Does that parameter work? And we had talked about this a bit yesterday. Saguenay, which is our big outlier earthquake, doesn't show up as a unusually short source duration. So there's a valid question whether this is doing it or not. The other way this has been looked at is looking at MB-MW relations as a measure of sort of high frequency versus energy versus the long period part. Bohr and Dewey are working on this. We're not going to talk about this today, but this will be another way we'll try to see if there's a difference in this variability for active regions versus stable regions. From the EPRI study, we recommended taking that standard deviation from the point source stress drop parameters that Gail had got, so that 0.43 number as our inter-event standard deviation. So it's a little bit bigger than the West, but not a lot bigger. We also had the other part, the intra-event term. So we did this here. Ideally, you'd have a lot of data on which to compare this. We simply looked at the effects of crustal structure differences and used simulations. So the red here are 3 different crustal structures we had for California, active regions. These green are 12 different crustal structures that were developed as part of the EPRI 93 Eastern study. So these are representative of different parts of the East. And then if we look at as well what impacts the variability is the depth that we end up using. These are the depth distributions in the East are in blue, in California are in green, and so we don't have as deep of earthquakes. And we compared as well to European models, which are more like the California case. So we would expect a little additional variability due to a broadening of the depth distribution in the East. Well, we then took a lot of simulations for the different depth distributions and different crustal structures. Each one of those was fit to an equation, and we're going to now look at not the variability here. This would be part of our path term already. that we talked about before. But this is now going to be, we want to look at the differences between different models, different crustal structural models. And when we do, and we did the same thing for the active regions. And when we do that, we see our standard deviations due to propagating or using different crustal structures are here on the order of 0.2 to 0.3, and in the stable regions they're a little bit smaller, if anything, than that. The suggestion from this is that we don't expect greater variability in the east due to regionalization than we would expect in the active regions. So if we had lumped all the active regions together, we would have had a standard deviation that's already capturing those effects. I'm going to skip site term variability. The depth effect was something Gabe had talked about, and I'll show again here because this ended up being an important piece for us. If we use joiner bore distance metric, which is what has been used in the EPRI models, then if I had a source here, the same magnitude, say 5 earthquake, whether it was horizontal distance of 5 kilometers away, but whether it was 2 kilometers or 20 kilometers deep, the joiner bore distance is all the same, and the equation we're using would have predicted the same ground motion for those. But if we think that it's actually the hypocentral distance that's important, we would have expected these to be larger ground motions here that are closer. The ones that are deep, we would have had smaller ground motions, and we would have got this variability, additional variability in our ground motions due to depth variability. Okay? If you plug that into the standard deviations, and this is what Gabe had talked about, at large distances, here's our standard deviation, a little over 0.6. Then you propagate that back in close, that's that same depth term that Gabe showed of the standard deviation ramping up. So now you get up here to numbers of 0.8. This starts to be a significant difference if you're getting the hazard controlled by close-in earthquakes. Okay? So now is that correct or not? So propagating this assumed that the source properties of these earthquakes are all the same. Okay, that is, it didn't worry about any correlation of terms. If we had gone and looked at this, this is a plot I actually did early on in the NGA project. It was my intent to show this to Dave Bohr and say, see, stop using joiner bore distance. It didn't work out that way, though. So what I did is looked at the residuals from an early version of my model with joiner bore distances less than 10 kilometers. So these are the intra-event residuals, right? Those are the psi terms. And said, if I look at just the close-in ones, and now I'm going to plot, so think about a bunch of ground motions here, but then plotting it versus the depth of the hypocenter. So if I'm looking at this, the deeper, if they were shallower hypocenters, I would have expected stronger shaking, right? Because if I go back here, I have a shallow hypocenter, I still use this horizontal distance and didn't take into account how shallow it is, right? So this, I'm using effectively a slant distance down to here on average. And so I would have expected more energetic ground motions here, and the one that's deep, they would have attenuated before they got to the surface. So I would have expected to see positive residuals, okay, larger ground motions at the shallow depths, and then at the high depths, negative ground motions. So I should have seen a slope like that, showing you the poor performance of the joiner bore distance metric. Okay, so it goes the wrong way, and if anything, the slope is the other way around. So it says, what's going on? If we look at the other panel, this is now inter-event residual. So these are my A to I's. Okay, and this is versus hypocentral distance, and we start to see that the deeper earthquakes tend to have a value that's larger than the shallower earthquakes. The implication is, in a simple way to think about it, is that the deeper earthquakes have higher stress drop. Okay, so going back to here, my assumption that these earthquakes had the same distribution of source property was wrong, and now I have a correlation of depth with, say, stress drop here. And if you ignore that correlation, you bring this standard deviation up. If you kept that correlation in there, we get basically a flat standard deviation. So really, a recurring theme is we need to track the correlations of our source parameters if we're going to start propagating these uncertainties with the numerical simulations. Okay, finally, so what we had said from our conclusions, that greater than 20 kilometers, we thought the intervent sigmas were okay to use. We didn't see We had a little increase to account for the frequency content difference. Effectively, instead of having the sigma dive down after about 10 hertz, we kept it high until here 25 hertz before it starts to come down. We did have a few alternative models for path effects, either saying that they're similar to the U.S. or Western U.S., or they were actually a little bit more homogeneous, but this is a small amount, 0.03. And really, what I would say here are the version of the NGA models we were looking at that time did not include magnitude dependence. We recommended using that version of the NGA models, essentially saying our conclusion was the NGA model sigmas could be transferred, but we didn't address the issue of magnitude dependence. And so we're still, I think Gabe left this as an open issue. Do we have a magnitude dependent sigma or not? And we'll talk about that in the next series of talks. So let's see. We did say to take out this correction to the sigma for short distances. We felt that the no increase at short distances was our preferred model. That is a strong enough correlation of stress drop in depth with that counteracted the increased distance, and we gave that a higher weight. We also had the model, which was the old one, where the stress drop is independent of depth with a small weight of 0.1, and then we stuck a model right in between. That we had some European data that sort of fell in between these two, and we gave those the 0.3 weights. So these here give us a big range of our sigmas in close that we're still not sure of, and to get at that we need to start to address the depth dependence of stress drop. These were the three adjustments that we ended up using close in, either no adjustment, the full adjustment with 10% weight, or something in between. And it's just at close distance. So, is sigma magnitude dependent? As I said, after we had done this, the NGA models were revised. Mine was one of them, to include magnitude dependence. As I said before, based on inclusion of aftershocks, that's really what drove you to that model. And you're going to see this next by Linda and Brian. And this is what those standard deviations look like. This is at magnitude 7. Let's say our 5 NGA models all had fairly similar standard deviations as a function of period here. If we looked at smaller magnitudes, they're very different. The two that kept them constant are still like this, whereas the others that had magnitude dependence bumped this up on the order of 0.1 to 0.2 magnitude units. And that's what we really need to get at here. So issues that we need to address moving forward. Again, we have a framework for calculating sigmas from the simulations, and we'll apply that. But a second issue is going to be, can we be taking Western U.S. or active region sigmas and applying them to stable continental regions? Or what sort of corrections have to be made? Can we look at other parameters to look at teleseismic data instead of just half duration, and really say, are these truly correlated with what we're after, the intervent residuals? Okay, are they good predictors of what we're after? You could be looking at stress parameter distributions for smaller earthquakes in the east and in the west to see if their sigmas are similar. Again, magnitude dependence is an issue. For the intra-event part, we could start to look at, again, sigmas from small earthquakes in the east and the west, looking at their intra-event terms in the sort of 100 or 50 to 100 kilometer range, and see if there's regional variations in these in the east, or if these numbers are similar, and back to magnitude dependence. So there's, I think, still quite a bit that we need to do to address the basic question, can we pick up our sigmas and move them from active regions to stable regions? And that's it.
Great. Thank you very much, Norm. Great. Thank you very much. So, any question for Norm on EPRI 2006 study? Peggy? Yeah, please. There is a button underneath. No. Yeah. Push that. Once. Yeah. You push it. Just. Okay. All right.
So for the very close-in recordings of earthquake, why do you automatically assume it's a stress drop and not just Q, which increases clearly with depth?
I don't. It's easier for me to think of it as stress drop. The inter-event terms that we looked at are over measured over stations that are not just close in, but out to 50 or 100 kilometers. But it could be something else. So I wouldn't say we know exactly what it is. We just say those earthquakes are propagating either more generic or propagating the energy more efficiently than the shallow earthquakes are. But remember, all we have is R in our simple ground motion models. Q doesn't show up in that term.
Yeah, no, it doesn't show up very much in ours either, but it's clearly, I think it's more Q than stress drop. But that's a seismology opinion.
The Q would have to be pretty strong over 10 kilometers to give you...
It is.
Okay. So I have the people telling me it is. So.
Frank?
I think the results from the Swiss analysis of the weak motion data showed that it's impossible to really separate these two causes. We just saw examples of an analysis of a large number of small earthquakes, and people have tried to separate these two effects, and it's simply not possible.
So in the end, we'll just say in our parameterization with R, something has to happen that there is a correlation between what comes out from the shallow depths and at the deeper depths.
Vladimir?
Norm, you discussed, in this presentation we see a lot of dependency on magnitude. What do you think? Some people say that sigma is also distance dependent. What are your thoughts about distance dependence?
My thoughts on this, I think, our emphasis usually in active regions is within 50 kilometers. And within 50 kilometers, I think the distance dependence at short periods is pretty weak. You get a stronger distance dependence at longer periods. If you start to look at a distance dependence from 50 to 100 to 1,000 kilometers, I don't even know what to say at this point. I'd be surprised if it's not distance dependent going at those large ranges. So we're going to have to do something different when we're looking out at these larger values. Empirical data, at least from the small magnitudes, are going to have to help guide us as to how you transfer stuff from our typical ranges out to hundreds of kilometers. So I think we will end up with a distance dependence.
More questions for Norm? No question? All right. Thank you very much, Norm. I appreciate that.